Hello everybody, and welcome again to Chemistry 103. Last time we left off with our discussion of chemical reactions and the proper way to balance them, and we stopped at this slide, counting particles by weighing. Today we are going to get into quantities in chemical reactions. We're going to introduce the idea of formula mass and the mole, and the idea of counting large numbers of particles with units that contain large numbers of particles. So the quiz will concern all of the material in this set of slides, except for the electrochemistry portion. That is merely for your personal edification. You won't be tested on it. It is fairly useful information for some of you if you're going into some kind of industry, but yes, it won't be on the test. So, counting particles by weighing. So, the baby example that we use here to introduce this concept, if you have a box of hexagonal nuts and you want to count out 500 of them, you could sit there and count out all 500 nuts individually, which would take a while, or you could weigh a small number of nuts, figure out how much each nut weighs by dividing the weight of, say, 10 hex nuts by the total weight. So say 10 hex nuts weighs 105 grams. That means that each hex nut weighs 10.5 grams. So then, in order to get 500 hex nuts, you would multiply that 10.5 grams by 500, and you would have a weight that corresponds to 500 hex nuts. This would make it significantly faster, especially if you knew the hex nut weight ahead of time, for you to pull out 500 hex nuts or 1,000 hex nuts or any number, without having to put too much effort into ascertaining the exact number. And then obviously keeping in mind that when you do this, you're obtaining an average weight for the hex nut, because not every hex nut is exactly identical. They have slight variations in their size and mass, but on average they will all be about the same. So in this example, 500 hex nuts would weigh 5,250 grams. So then you could take a scale and weigh out 5.25 kilograms of hex nuts, and you would have approximately 500 of them. In the same way, we can use atomic mass to count atoms. And we do this by making a number of simplifying assumptions and defining terms ahead of time to make our lives easier. In general, it is understood that atoms are incredibly small, much smaller than can be seen with the naked eye, and therefore much too small to count. There's the other factor of, within a given element, you may have different isotopes of the same element, and that will cause the actual average mass of a naturally occurring sample of that element to possibly differ from the mass of the most common isotope. So for instance, with carbon-12, the most commonly occurring natural isotope of carbon is the one that weighs 12 atomic mass units. However, there are also carbons that weigh 13 atomic mass units, and a tiny amount of carbon-14, which weighs 14 atomic mass units, and both of those average into what's called the molecular weight of carbon, which makes it the average weight 12.01 instead of 12.00. In general, grams are much too large to use to measure an atom, and so we have devised something called the atomic mass unit. One atomic mass unit is 1.66 times 10 to the minus 24 grams. Now that, as you can probably tell, is astronomically small. However, it becomes much more useful when dealing with chemical reactions, and it allows us to define some standard relationships. I mentioned a moment ago the idea of atomic mass and formula mass. So if you have a sample of atoms, even if they're all one element, they exist as a mixture of isotopes, and so the formula mass listed in the periodic table is given as a weighted average of the atomic mass. The example shown here is chlorine. It's given an average mass of 35.453. This is because there are two isotopes of chlorine, one that weighs 35 and one that weighs 37 AMUs, and the weighted average of their relative abundances causes the average mass to be 35.453. This number will appear below the chemical symbol in many printed periodic tables. In our periodic table that we've been using that has all of the information you could possibly want on it, you can choose to have the mass displayed, or you can also choose to have other properties displayed. So, atomic masses are determined on a relative scale. This means that you have to provide a reference mass that is rigorously defined, and in this case we use carbon-12. So carbon-12 isotopes have exactly a mass of 12.000 AMU, and all other masses in AMUs are defined based on this definition. So you see on the right here there are a number of average formula masses for a number of different elements, and notice many of these are not neat whole multiples of 1 AMU, mostly due to the naturally occurring presence of different isotopes. But even the different isotopes here that are shown do not have exactly whole numbers of AMUs because of slight discrepancies in the mass of a neutron and a proton. So it turns out that the basis of nuclear physics comes from the fact that when energy is bound up in a nucleus, it converts into mass, and when mass can be lost by the breaking apart of nuclei, and that energy discrepancy comes in the form of small decimal differences from 1 AMU for protons and neutrons in heavier elements. That's all very complicated, and you don't need to memorize any of that, but that's the explanation for why neon 20, for instance, has a mass of 19.99 AMU. The binding energy in the nucleus between neutrons and protons causes the mass to be slightly lower. So you can use the atomic mass to count atoms by understanding how much an AMU is in grams and using that relationship to find out how many atoms are in a specific mass. So one of the main ways that we measure things in chemistry is by weighing them. So you say you have a sample of an element and you have a mass for that element that you've measured with a balance. You can determine how many atoms are in that sample using the conversion factor of the atomic mass. So, for example, nitrogen has an atomic mass of 14.01 AMU. And it's important to remember that this is nitrogen atoms, not nitrogen molecules, which have twice that mass. So, one nitrogen atom weighs 14.01 AMU, and that means that we have the following conversion factors when we're dealing with atom counting situations. So for every 14.01 AMU, there is one nitrogen atom, and for every one nitrogen atom, there is 14.01 AMUs of mass. So here's another example. Say you have 1 gram of lead. How many atoms of lead are present? So we have 1 gram of lead, and we know that 1 atom of lead weighs 207.2 AMUs from our periodic table. This is the average mass because we have just a sample of unpurified, anisotopically pure lead. Now we also know that 1 AMU is equal and defined as 1.66 times 10 to the minus 24 grams. And then the conversion is straightforward. 1 gram of lead divided by 1.66 times 10 to the 24 grams of lead per AMU times 1 atom of lead per 207 AMU. The grams cancel, the AMUs cancel, and you're left with 2.9 times 10 to the 21 atoms of lead. So whenever you divide by a negative exponent, the exponent becomes positive, but then you're dividing by 200, so that reduces the total exponent by 3. Here is another example. So we're going in reverse this time, calculating the mass in AMU of 1 times 10 to the 4th carbon atoms. That's 10,000 carbon atoms. So we are given 10,000 carbon atoms. We need to develop a plan to convert from atoms to AMU, and then develop our conversion factors. So 1 atom of carbon, and this is the average mass of carbon, is 12.01 AMU. And that means that for every carbon atom, there are 12.01 AMUs of mass. Now we set up the problem. 1 times 10 to the 4th carbon atoms times 12.01 AMU per carbon atom. Carbon atom units cancel, and we are left with 1.2 times 10 to the 5 AMUs. Now we could go further and figure that out in grams by multiplying the AMUs by the gram definition of an AMU, but I'll let you do that on your own. So now we're going to get to the idea of formula mass, and we're going to break that down a little bit. So the formula mass is when you take the atomic mass of all of the atoms in a molecule and add them together, and this gives you the average mass of that molecule. This allows us to do calculations with regards to chemical reactions and their completeness. It also lets us properly choose our reactants so that reactions will go to completion. And we can calculate a formula mass for both compounds and diatomic molecules, diatomic elements such as oxygen and nitrogen. So we calculate the formula mass of calcium chloride, for instance, by writing the formula from the name given. So calcium chloride in this case, we have calcium 2+ because the metal is from group 2, and chloride has a -1 charge because it's from group 7. So the formula is CaCl2 because we have to maintain charge balance, and therefore the formula mass is the sum of the atomic masses of atoms in the formula, which means that there is 1 calcium atom and 2 chlorine atoms. So 1 calcium atom weighs 40.08 AMUs, 2 chlorine atoms weigh 35.45 AMUs each, and the atoms cancel. So the total mass is 40.08 plus 70.9, which yields 110.98 AMU. And that is the formula mass of calcium chloride. Now, because the mass of atoms are so small, and there are so many of them present whenever a chemical reaction occurs, we like to introduce a counting quantity that accounts for incredibly large numbers of particles while still retaining some kind of physical generality that is standard across all elements. So we have devised, just as in this case of something like paper, you have reams of paper or dozens of donuts or pairs of shoes, we have a unit for atoms, and we call it the mole. So a mole is 6.022 times 10 to the 23rd particles or objects. And this number is called Avogadro's number, and it is the number for which it's the number that if you multiply the atomic mass in AMUs, it gives you the molecular weight as the same number. And I'll explain that more. So the weight of 1 mole of the element in grams is equal to the atomic mass in AMUs. So it's a convenient unit that provides a straightforward relationship between something called molar masses, which are given in grams, and atomic masses, which are given in AMUs. So an atomic mass is the mass of 1 particle of an element, and the molar mass is the mass of 1 mole of that element. And those numbers are the same magnitude because of Avogadro's number. So we're going to go through and do some calculations using moles, because it's going to become the most important quantity of your Chemistry 103 lives. So, how many molecules of bromine gas are present in 0.045 moles of bromine gas? So bromine gas is Br2, because bromine exists as a diatomic molecule. So 0.045 moles converted to molecules goes through Avogadro's number. So we have the equality: 1 mole equals 6.022 times 10 to the 23rd molecules of bromine. So if we turn those into conversion factors, they become fractions, and we pick the one that is arranged properly for our problem. In this case, it happens to be the one with the large number in the numerator and moles in the denominator. So now we set the problem up. So we have 0.045 moles of bromine times 6.022 times 10 to the 23rd molecules of bromine per mole of bromine. The moles cancel, and we are left with 2.7 times 10 to the 22nd molecules of bromine. So still a very large number of molecules, but notice that our number of moles was small enough that scientific notation was not needed. So this brings us to a very convenient idea. In a chemical formula for a molecule, the subscripts equal the number of atoms present in the compound, but it can also mean the number of moles of the atom present in 1 mole of the compound. So, for instance, the molecule glucose, C6H12O6, has 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen, but it also has 1 mole of glucose has 6 moles of carbon, 12 moles of hydrogen, and 6 moles of oxygen. So now we're going to calculate the number of moles of carbon atoms present in 1.85 moles of glucose. So, we have given the moles of glucose, and we're looking for moles of carbon atoms. So we start by figuring out what the subscript of carbon in glucose is. We just saw the glucose molecule, but we'll have it again here. So 1 mole of C6H12O6, which is glucose, contains 6 moles of carbon atoms. Therefore, we have as a conversion factor 6 moles of carbon atoms per mole of glucose, or 1 mole of glucose per 6 moles of carbon atoms. Now when we set up our problem, we have 1.85 moles of glucose times 6 moles of carbon atoms per mole of glucose. Moles of glucose cancel, so the math is 1.85 times 6, which equals 11.1 moles. So in 1.85 moles of glucose, there are 11.1 moles of carbon atoms. And now that we've introduced the idea of the mole, we can talk more about molar mass. So this is where the carbon-12 atom comes into play. Carbon-12 is defined as a 12 AMU mass. And therefore, if you multiply 12 AMUs times Avogadro's number, you get 12 grams. This is the basis of molar mass. So by this ratio, 1 mole of any element is the amount of atoms or molecules or ions that is equal to its atomic mass in grams. And any such mass contains 6.022 times 10 to the 23rd particles of that element. And then you can get this mass from any periodic table by looking at the element in question. So, here are some examples. 58.5 grams of table salt is 1 mole, because the molar mass of sodium chloride is 58.5. Similarly, 201 grams of mercury is 1 mole, or 63.5 grams of copper, or 254 grams of iodine, or 342 grams of table sugar, 180 grams of aspirin, and 18 grams of water. All of these samples contain the same number of particles, but because those particles have a different mass, the masses of each of these equal numbers of particles is different. So, now that we've talked about molar masses, we can start applying this to our knowledge of compounds. So, iron sulfate, we are going to find its molar mass. We know that iron 2 sulfate has a formula of FeSO4 because iron 2 means that it is a positively 2 charged ion, and that sulfate is -2 charged all the time. So we start by calculating the molar mass of each element in the compound, and then multiply that mass by its respective subscript, which is equal to the number of moles in 1 mole of that compound. Then the molar mass is calculated by summing the molar masses of each element. So, the formula is FeSO4, and the molar masses of iron, sulfur, and oxygen are 55.85 grams of iron per mole, 32.00 grams of sulfur per mole, and 16 grams of oxygen per mole. Then we multiply each molar mass by its subscript. In the cases of iron and sulfur, that subscript is 1, but in the case of oxygen, it's 4. So the mass of oxygen in the compound is 64.00 grams, with the moles all canceling. And then you find the molar mass of the compound by adding the mass of each element. So 55.85 grams plus 32 grams plus 64 grams equals 151.85 grams. Now, there are 3 quantities that you generally calculate using molar mass. You're either calculating the number of particles you're calculating the number of moles, which is still technically the number of particles, or you're counting the number of grams. And this conversion is one of the fundamental building blocks of our study of chemistry, because you can move back and forth between different quantities of reactants and products and make predictions based on your understanding of how particles are collected. So, if you have moles of a substance and you use Avogadro's number, you can find the particles of a substance. You can, if you have moles of a substance and you have use the molar mass, you can find the grams of a substance. Now, if you have the grams of a substance, you can use molar mass to convert to moles of a substance, and then Avogadro's number to convert to particles of a substance. So you can find out precisely how many particles of an element that you are putting into a reaction, for instance, or are being produced by a reaction. So, here is a nice real-world example. International Foods coffee contains 3 milligrams of sodium chloride per cup of coffee. How many moles of sodium chloride are in each cup of coffee? So we have 3 milligrams of NaCl, sodium chloride, and we're looking for moles of sodium chloride. We use the fact that 3 milligrams is converted to grams by dividing by 1,000, because there are 1,000 milligrams of sodium chloride per 1 gram of sodium chloride. Milligrams cancel, and then we have 0.003 grams. Now we have the molar mass of sodium chloride is the mass of 1 sodium atom and 1 chloride ion, which is 22.99 plus 35.45. This is equal to 58.44 grams per mole. That's the molar mass of sodium chloride. And therefore, we have the equality 1 mole of sodium chloride equals 58.44 grams. We have the conversion factors, and this allows us to convert grams into moles by putting moles in the numerator and grams in the denominator. The grams cancel, and 0.003 divided by 58.44 is 5.13 times 10 to the minus 5 moles of sodium chloride. Here's another one. Ethylene glycol, or antifreeze, has the formula of C2H6O2. How many molecules are present in a 3.86 times 10 to the minus 20 gram sample? So this seems like a very small mass. However, we will convert grams to moles using the molar mass of ethylene glycol, which requires us to then use Avogadro's number to find the number of molecules. So the first equality is that 1 mole of C2H6O2 is 62.05 grams. This could easily be found by adding the mass of 2 carbon atoms, which is 12 times 2 is 24, plus 6 hydrogen atoms. 6 times 1 is 6, bringing the total to 30. And then 2 oxygen atoms weighs 32, so 30 plus 32 is 62. And the little bit of decimal left over is because of the slight differences from whole numbers of the various masses. So our first conversion factor is 62.05 grams of ethylene glycol per mole. And our second equality is that 1 mole equals 6.022 times 10 to the 23 molecules. And our second conversion factor is that written as a fraction. So if we multiply 3.86 times 10 to the minus 20 grams times 1 mole per 62.05 grams times 6.022 times 10 to the 23 molecules per mole. The grams cancel, the moles cancel. We do the multiplication and we end up with 375 molecules. Now, there's this other useful concept called percent composition. Sometimes it's useful to know the composition of a compound in terms of what percentage of the total weight corresponds to each element, because you might only be able to determine the weight percent because of various experimental limitations, but you'd still like to be able to know some information. So percent is more generally parts per 100. So it's just the whatever quantity divided by 100, or rather setting 100 as the total. So say you have $50. $50 is 50% of $100 because 50 out of 100 is 0.5. Another example, in case you don't know how to calculate percents. 4 oranges and 5 apples. What percent of the total is oranges? So you divide 4 by 9, and then you multiply by 100. It's 44%. So 4 divided by 9 is 0.44, times 100 is 44. So percent composition is the percent by mass of each element in a compound, and it can be determined by its chemical formula and the molar masses of the elements that compose the compound. So the total percentage should add up to 100, and the percent of each element contributes to the mass of the compound. So the mass percent of each element in a compound is the mass of the element divided by the molar mass of the compound times 100. So we're going to do an example of this. Percent composition of each element in ammonium hydroxide, NH4OH. So first we determine the contribution of each element. We have 1 nitrogen atom, which weighs 14.01 grams per mole. We have 5 hydrogen atoms, which weigh 1.0078 grams per mole, for a total of 5.04 grams per mole. Then we have oxygen, which occurs once at 16.00 grams per mole, and therefore the total is 35.05 grams per mole. Now, to find the mass percent, we divide each individual element by the total mass. So in the case of nitrogen, we have 14.01 divided by 35.05 times 100 equals 39.97% nitrogen. And likewise, hydrogen is 5.04 divided by 35.05 times 100, and that brings us 14.38% hydrogen. And then oxygen is 16.00 divided by 35.05 times 100, and that equals 45.65% oxygen. And that is by percent mass. This is useful in conjunction with the concept of empirical formulas. The empirical formula is the simplest ratio of elements in a compound, and it uses the smallest possible whole number ratio of atoms present in a formula unit. If you know the percent composition, you can calculate the empirical formula. And this may not be the same as the molecular formula, but it gets you close. It's useful in the lab, especially when dealing with unknown chemicals. So to determine an empirical formula, you calculate the number of moles of each element using the molar mass or the atomic mass. Then you calculate the ratios of the elements to each other, and you find the lowest whole number ratio and divide each of those numbers by the smallest number of moles present. And that will give you the ratio of elements to one another. It's important to remember that subscripts in a formula are always whole numbers, never decimals. So the numbers that result from this calculation become the subscripts of the element. If you end up with numbers that are not whole numbers, you have to multiply the whole molecule by a small integer until you obtain a whole number. So small integers are 2, 3, 4, 5, or 6. And once you have an empirical formula, you can relate it to the molecular formula by dividing the molar mass by the empirical formula and figuring out what whole number multiplier you need to use to get the molecular formula. So we're going to do an example of this after we've looked at a couple of these common molecules. So in order to, once you have the empirical formula and you know your factor, your whole number multiplier, then you can multiply the empirical formula by the factor to get the molecular formula. Something like carbon dioxide, its empirical formula is the same as its molecular formula, so the factor N is 1. However, something like oxalic acid, the empirical formula is HCO2, but the actual molecular formula is H2C2O4, so N in this case would be 2. Dinitrogen tetroxide is NO2 times 2, which would be N2O4. Benzene has an empirical formula of CH, but an actual molecular formula of C6H6. So that's the N in this case would be 6. The same with glucose. Glucose is CH2O in the empirical formula, but its actual molecular formula is C6H12O6, so that's a multiple of 6. Now we're going to unify all these concepts that we just learned into a nice example. So lactic acid, it's a commonly occurring biological molecule. It has a molar mass of 90.08 grams and a percent composition of 40.0% carbon, 6.71% hydrogen, and 53.3% oxygen. How do we find the empirical and molecular formulas of lactic acid? So we start by assuming a 100 gram sample size. So we will convert our percents to grams and then convert the mass of each element to moles. Once we've converted the mass to moles, we'll divide the mole quantity by the smallest number of moles to gain whole numbers of ratios so that we can put them into our formula. So in this case, 40 grams of carbon times 1 mole of carbon per 12 grams of carbon gives us 3.33 moles of carbon. 6.71 grams of hydrogen times 1 mole of hydrogen per 1.008 grams gives us 6.66 moles of hydrogen, and 53.3 grams of oxygen times 1 mole of oxygen divided by 16.00 grams of oxygen gives us 3.33 moles of oxygen. Now you could probably see that there is a common factor here. Obviously the grams cancel, leaving us with units of moles. And if we divide by the smallest number, it's 3.33. So 3.33 divided by 3.33 is 1. 6.66 divided by 3.33 is 2. So in this case, our ratio of carbon, hydrogen, oxygen is 1 to 2 to 1. Therefore, our empirical formula is CH2O. And the empirical formula mass is 12.01 grams for 1 mole of carbon, 2 times 1.008 grams for 2 moles of hydrogen, and 16.00 grams for 1 mole of oxygen for 30.03 grams per mole. Now, in order to determine our molecular formula, we obtain the value of N because we know the molar mass and we know the empirical formula mass. So we divide the molar mass by the empirical formula mass, and this gives us N, which in this case 90.08 divided by 30.03 is approximately 3. So N is 3. We multiply the empirical formula by 3, and we get C3H6O3. So, to review, formulas for compounds consist of the empirical formula, which is the smallest possible set of subscript numbers, smallest whole number ratio of elements, and this is the form in which all ionic compounds are given. So if you have a salt, in general, you'll be given the empirical formula of that salt because any size sample is going to contain repeating sections of that same empirical formula. But all of the bonds are identical. And then there are molecular formulas, which are the actual formulas for molecules, and it shows all of the atoms present in a molecule. They may be the same or different from the empirical formula. If they're different, then you obtain the molecular formula as a factor N times the empirical formula. So now we're going to talk about some properties of chemical reactions. We've mentioned before a little bit conservation of mass, but we'll reiterate. As a chemical reaction proceeds, reactants are consumed and new materials are produced with new chemical properties. However, the total number of atoms remains the same. Bonds are broken or formed, atoms are rearranged. This produces no new substances, but no material is lost or gained as the original substances change. This is actually a physical law that is never violated. The quantity of matter never changes. The sum of the masses of the products is equal to the sum of the masses of the reactants. And atoms are neither created nor destroyed. And that's in chemical reactions. Obviously, they are created or destroyed in nuclear reactions, but we already talked about those as much as we're going to talk about them in this class. So, a further extension of this law is that a balanced chemical equation has the same number of atoms on each side of the arrow and the same mass. Here's a common reaction, the reaction of methane with oxygen to produce carbon dioxide and water. If we balance this properly, it requires two oxygens in the reactant side, and it produces 2 waters in the product side. And this diagram shows that. This is a review of what we did last week, but we're going to get deeper into how to use these facts effectively. So, 1 mole of methane gas reacts with 2 moles of oxygen gas to produce 1 mole of carbon dioxide and 2 moles of water vapor. That's how that reaction would be read. If you multiply each of the molar masses by the coefficient, this will give the total mass of reactants and products. So in this case, you have 1 mole of methane and 2 moles of oxygen. 1 mole of methane weighs 16.04 grams because carbon weighs 12.01 and hydrogen weighs a little less than 1.01. And there are 4 of them. And then 2 moles of oxygen gas weigh 64 grams because each O2 molecule weighs 32. Therefore, the total mass of reactants is 80.04 grams. Now, on the product side, we have 1 mole of carbon dioxide gas and 2 moles of water vapor. So 1 mole of CO2 weighs 44.01 grams because 12.01 plus 16 plus 16 equals 44.01. And 2 moles of H2O vapor is 36.03 because 2 hydrogens weighs a little more than 1, and oxygen weighs 16. The total mass in this case is also 80.04, which satisfies the law of conservation of mass. So this is why chemical equations are written, because it tells us the relative number of atoms reacting and produce. And this could be in either in terms of single particles or in terms of moles. Here's another reaction: carbon monoxide gas plus hydrogen gas to yield methanol liquid. In this case, you need 2 moles of hydrogen gas to react with 1 mole of carbon monoxide to produce 1 mole of liquid methanol. So, in order to make predictions about the quantities required for these chemical reactions, you must take into account the idea of converting from moles of one substance to moles of another substance. This is determined by the values of coefficients. So, how do we determine the number of moles of methanol produced if we have 0.295 moles of hydrogen gas? Well, we have to make a mole-to-mole conversion and convert the given mole amount of hydrogen gas to the needed mole amount of methanol. Because we've balanced our equation, we know that for every mole of methanol, we need to consume 2 moles of hydrogen gas. And also, for every mole of carbon monoxide reacted, we need to consume 2 moles of hydrogen gas. And for every mole of carbon monoxide consumed, we produce 1 mole of methanol. So, more about mole-to-mole factors. So, if we write out all of the possible mole ratios for the following chemical equation, we see hydrogen gas plus oxygen gas makes water. We have to put a 2 in front of the hydrogen gas because we have to break up the oxygen molecule to make 2 water molecules. This allows us to have 4 hydrogens and 2 oxygens on each side of the equation. And it also tells us that for every 2 moles of hydrogen gas reacted, we react 1 mole of oxygen gas. And the converse is true. For every mole of oxygen gas reacted, we have to react 2 moles of hydrogen gas. Also, for every 2 moles of hydrogen gas reacted, we produce 2 moles of water. And you can flip that in the other direction. For every 2 moles of water produced, we have to consume 2 moles of hydrogen gas. And then, for every 1 mole of oxygen consumed, we produce 2 moles of water. Or for every 2 moles of water, we must consume 1 mole of oxygen gas. So we do calculations based on balanced equations. This allows us to use mole-to-mole conversions to figure out the number of moles of one substance that we need based on the number of moles of the known substance. We have to make sure these equations are balanced, and we have to identify the known and needed substances and convert them based on this equation. So given number of moles times needed number of moles divided by given number of moles. This process is called stoichiometry. So we use mole ratios from balanced chemical equations to convert moles of one compound to moles of another compound in the following way. So we start with grams of A. We use the molar mass of A to convert to moles of A. So you say you weigh out 10 grams of your reactant. You can figure out how many moles that is. And then based on your chemical equation, you should be able to find out from the stoichiometry or the coefficients in the reaction equation how many moles of A correspond to how many moles of B. Once you've figured out how many moles of B that you need, then you can use the molar mass of B to figure out how many grams of B you have. Moles of B per moles of A is known as the mole-to-mole factor. So, how many moles of CO2 are formed when 4.3 moles of C3H8 or propane reacts with the required 21.5 moles of oxygen gas? So we'll start by balancing the equation, then we'll make a plan to convert the given amount of moles to the needed amount of moles. Then we'll use coefficients to state the relationships and mole-to-mole factors, and then we'll set up the problem using the mole-to-mole factors and cancel our units to get the final answer. So first, C3H8 reacts with oxygen to produce CO2 and H2O. The factors in this case, we need 5 oxygen molecules to react with one propane molecule to yield 3 carbon dioxide molecules and 4 water molecules. So therefore, we take our stoichiometry flowchart, and we insert our givens into it. So we're given 4.3 moles of C3H8. We need moles of CO2. So in this case, the mole-to-mole factor is 1 mole of propane produces 3 moles of carbon dioxide. So now we set up the problem using our mole-to-mole factor, and this cancels the moles and provides given moles and provides needed moles. So here's our equation again for reference. We're given 4.3 moles of C3H8. We need moles of carbon dioxide. Our mole-to-mole factor is 1 mole of C3H8 for 3 moles of CO2. 4.3 moles of C3H8 times 3 moles of CO2 per mole of C3H8. The moles of C3H8 cancel. We're left with 12.9 moles of carbon dioxide. So when 4.3 moles of propane are burned in oxygen, it produces 12.9 moles of carbon dioxide. So we can use this idea to make mass calculations for reactions. You can start with a known mass of a substance and then convert to moles, and then you can also start with a known number of moles and convert to a sought after mass, because you should in principle, if you know what the chemical equation is, you should know what the molar masses of everything in the equation are, because you know what the chemical symbols are. So, for a mass calculation, if you want to find the mass of a product from, say, the number of moles of a reactant, you convert the moles using the mole ratio as before. So the moles of the one substance corresponds to a number of moles of the other substance. And then you convert moles to grams using the molar mass. Now it's important to remember that moles and grams are not interchangeable in chemical equations, and that the ratios are not mass ratios but mole ratios. So you can't divide the one mass by another mass and you will get the wrong answer. So here's our flowchart again. Just to remind you, you need to convert from grams to moles using the molar mass or molecular weight. They're interchangeable terms for the same concept. So we're going to do another reaction. So we're going to use that same reaction of propane with oxygen again, but this time we're asking what mass of carbon dioxide is produced when 96.1 grams of propane react with sufficient oxygen. So when they say sufficient oxygen, that means that they're giving it as much as it needs to react all of the propane, and you don't have to worry about whether the reaction is limited in any way. So first we balance the equation as we did before. Then we make our plan to do our conversions. So we know that 1 mole of propane has a mass of 44.09 grams if you add up 8 hydrogens and 3 carbons. We know that CO2 has a mass of 44.01 grams. And we know that for each mole of propane, 3 moles of carbon dioxide are produced. So we're given 96.1 grams of propane. We need grams of CO2. And here's our flow chart. So propane is on this side, carbon dioxide is on this side. So 96.1 grams of propane divided by 44.09 grams of propane per mole yields 2.1796 moles of propane, which are consumed in this reaction. Now we know that for every mole of propane consumed, there are 3 moles of carbon dioxide produced. So 2.1796 moles of propane times 3 yields 6.539 moles of carbon dioxide. And we know that the molar mass of carbon dioxide is 44.01 grams, so 6.539 moles of carbon dioxide times 44.01 grams of carbon dioxide per mole. The moles cancel, and we are left with 287.76 grams of carbon dioxide. So when you burn propane, 96.1 grams of propane, you produce 287.76 grams of carbon dioxide. Here's another example. What mass of carbon monoxide and what mass of hydrogen are required to form 6 kilograms of methanol by the following reaction? We've looked at this reaction already once, so it should be familiar at this point. CO plus H2 yields methanol. We have to put a 2 in front of the H2 to make sure that the number of hydrogens is balanced on both sides of the equation. And we want to know how many grams of carbon monoxide we need to make and how many grams of hydrogen we need to make 6 kilograms of methanol. So 6 kilograms of methanol times 1,000 grams per kilogram is 6,000 grams of methanol. We also know that the molar mass of methanol is 32.04 grams, so 6,000 grams divided by 32.04 grams per mole yields 187.27 moles of methanol. And we know that the mole ratio of methanol to carbon monoxide is 1:1. So we also consume 187.27 moles of carbon monoxide. And we know that the number of moles of hydrogen consumed is 2 per mole of methanol. So we have to consume 374.53 moles of hydrogen in this same reaction. Now we go further. 187.27 moles of carbon monoxide divided or times 28.01 grams per mole of carbon monoxide means that we consume 5,245 grams of carbon monoxide in this reaction. And 374.53 moles of hydrogen gas times 2.0156 grams of hydrogen gas per mole means that we consume 754.9 grams of hydrogen gas in this reaction. Now we come to the idea of limiting reactants. So in nature, chemical reactions will occur until one of the reactants is used up. And there's almost never exactly enough of both reactants or all of the reactants to cause the reaction to go indefinitely. The reactant that is used up first is called the limiting reactant, or limiting reagent in some cases. And obviously, if you run out of reactants, this limits the amount of product that can be made with a given reaction. Here is a really simple example of that concept. If you have 2 hamburger buns and 3 hamburgers, you cannot make 3 sandwiches. You can make 2 complete sandwiches, and then you have 1 hamburger patty left, which means you're probably eating it with your hands. So in the same way, reactions do not always combine in exact mole ratios because lab conditions are often not perfect. Usually for this reason, you determine what the limiting reactant will be, and then you provide an excess of that reactant so that you use all of usually your more valuable component. And then the reaction will continue until one of the reactants runs out. So if you know what your limiting reactant is, you can calculate how many moles of product you will obtain by knowing the stoichiometry of your balanced reaction equation. So first you balance the equation, then you determine how many moles of each reactant you have, and then based on the mole ratio, you find out how many moles of product you could make if you reacted all of each reactant based on the mole ratios in the equation. Now, those numbers will be different. The smaller of the 2 numbers corresponds to your limiting reactant, and the smallest number is the maximum amount of product you can make in that reaction. So here's an example. Lithium nitride, which is an ionic compound which contains lithium plus ions and nitrogen 3 minus ions, or nitride ions. This is prepared by reacting lithium metal with nitrogen gas. So if you have 56 grams of nitrogen gas and 56 grams of lithium metal, what is the maximum amount of lithium nitride that you can make with this collection of reactants? So you start with the balanced chemical equation. Lithium solid plus nitrogen gas yields Li3N. And right off the bat, you can tell that you have to do some balancing in order to compensate for the nitrogens. So if you have 2 nitrogens on the reactant side, and each of them binds with 3 lithiums, then in order to make the number of nitrogens equal on both sides, you have to multiply the lithium nitride molecule by 2, and then in order to make the number of lithiums equal on the left-hand side, you have to multiply that by 6. If you have 56 grams of lithium and 56 grams of nitrogen, how many grams of lithium nitride do you make? Well, you have to convert from grams of lithium to moles of lithium, and then figure out how many moles of lithium nitride you would make from that many moles of lithium, which in this case, and then you do the same thing for nitrogen gas. So you have a number of conversion factors. 1 mole of lithium metal is equal to 6.941 grams of lithium, and 1 mole of nitrogen gas is equal to 28.00 grams of N2, and 1 mole of lithium nitride is equal to 34.83 grams of lithium nitride. And you have the conversion factor ratios that are those same equalities in fractional format. So 56 grams of lithium divided by 6.91 grams of lithium is equal to 8.07 moles of lithium. And for every mole of lithium, for every 2 moles of lithium nitride produced, there are 6 moles of lithium metal consumed. Multiply this fraction by 8.07 moles of lithium. The moles of lithium cancel, and we obtain 2.69 moles of lithium nitride from the reaction of 56 grams of lithium. Now for nitrogen, 56 grams of nitrogen divided by 28.02 grams of nitrogen per mole means that we have approximately 2 moles of nitrogen gas. And from the balanced equation, for every 2 moles of nitrogen gas, or for every 2 moles of lithium nitride, we consume 1 mole of nitrogen gas. We multiply that by our 2 moles of nitrogen gas to obtain approximately 3.997 moles of lithium nitride produced. So 3.997 moles is higher than 2.69 moles. So in this case, lithium would be the limiting reactant because there is stoichiometrically less of it than the nitrogen gas. So now that we know that lithium is the limiting reagent, we can calculate the number of grams of lithium nitride that will be formed in this reaction, because we know that there will be 2.69 moles. So 2.69 moles of lithium nitride times 34.83 grams of lithium nitride per mole. Moles cancel, and we have 93.7 grams of lithium nitride produced in this reaction. And of course, because chemical reactions are never perfect, this number that we just calculated is known as the theoretical yield. So that's how much you should produce given perfect situations and complete reaction of the non-limiting reagent. However, this will not always occur due to a lot of different factors, mainly side reactions or material losses during transfer or spills. Other things that can happen is you can evaporate things. So the maximum amount of product will always be less than the theoretical amount that you calculate. So if you want to obtain your percent yield, you divide your actual yield by the theoretical yield and multiply it by 100. So the example for our previous problem, say you only actually produced 90.8 grams of lithium nitride. What is the percent yield? You've already calculated your theoretical yield, which is 93.7 grams, and your actual yield is 90.8 grams. You divide 98.8 by 93.7 and multiply by 100. You have achieved a 96.9% yield for this reaction. Now that we've talked about chemical reactions and the quantities involved in them, we will get into the last relevant topic, which is energy released or consumed by reactions. So just as elements and compounds can be reactants in a chemical reaction, you can also have heat as a reactant or a product. So the energy change due to the breaking or formation of bonds is referred to as heat of reaction or enthalpy. And the enthalpy change is the amount of heat produced or consumed by any process, but specifically a chemical process. You've probably seen this reaction diagram before. There are two types of heats of reaction. Endothermic reactions are reactions that absorb heat, and this means that delta H is positive. This is shown on the right. You have reactants which are at low energy, and then you add their activation energy. They react to form products which have a higher total energy than the product had. This difference is called the heat of reaction, which is absorbed. In an exothermic reaction, these produce heat while occurring. This is something like a combustion reaction, for instance. This causes delta H to be negative, which indicates that heat is evolved by the reaction. So this diagram, you have high energy reactants. You overcome an activation energy barrier to cause the reaction to occur, and then once the reaction is finished, the total energy of the products is lower than the energy of the reactants. And we say that the heat of reaction has been released. Two complementary examples of this are photosynthesis and cell metabolism. So in photosynthesis, you combine carbon dioxide and water using sunlight to produce glucose and oxygen. And that has a heat of reaction of positive 2,801 kilojoules. Now in cell metabolism, you take glucose and oxygen and you react them together to produce carbon dioxide and water, like so. And this evolves 2,801 kilojoules of energy. Now we're going to do an example. So sulfur dioxide reacts with oxygen in a combustion reaction to produce sulfur trioxide. Calculate the heat produced when 75.2 grams of sulfur trioxide is produced. So for this, you need to know what the heat of the reaction is, which will be given. We have two SO2 molecules plus one O2 molecule yields two SO3 molecules. And the heat of this reaction is minus 99.1 kilojoules, which means that it releases 99.1 kilojoules of heat. So we're given that there are 75.2 grams of SO3, and we need to convert this to the heat produced when this much SO3 is formed. So in order to establish this relationship, we have to do a number of conversions. We have grams of SO3. We need to convert that to, using the molar mass, to moles of SO3. And then we need to use the heat of reaction to find the number of kilojoules. So, necessary conversion factors in this case are 1 mole of SO3 weighs 80.07 grams, and for every 2 moles of SO3 produced, 99.1 kilojoules of heat are evolved. So now we set the problem up. We have 75.2 grams of SO3 divided by 80.07 grams of SO3 per mole. The grams cancel. Then we multiply by 99.1 kilojoules per 2 moles of SO3, and the moles of SO3 cancel. And then we multiply through to get 46.5 kilojoules. So 46.5 kilojoules of energy are produced when 75.2 grams of SO3 are produced via the combustion of SO2 gas. And that is all you need to know about chemical reactions and the quantities involved in them. We will use the information that we've learned in chapters 7 and 8 to dig deeply into the various types of chemical reactions that occur and the processes that we see in our daily lives. Next week, we're going to talk about the gas laws, and we're going to tie up some final pieces of our understanding of matter before we dip into some of the harder stuff that we'll finish out the semester with. Thanks for tuning in, and I hope everything remains understandable to everybody.